Hi, and welcome. We'll be considering nets of higher dimensional cubes today. My name is Satyan Devadoss, and this work is joint with my students Kristin DeSplinter, Jordan Readyhough, and Bryce Wimberly, who are scattered all over the US right now. And our work is actually motivated by considering a very old and classical problem of unfolding convex polyhedra. So given a convex polyhedron like this, like the soccer ball, there's an open problem motivated by Dürer, made clear by Shepard, which asks, does every convex polyhedron have an edge unfolding without overlap? In other words, can you cut along certain edges of this polyhedron, unfold it, lay it flat on the plane so that the faces don't overlap? So here's one possible unfolding of this polyhedron. So the question is, can you do this for every polyhedron imaginable? And surprisingly and wonderfully, this problem remains absolutely open. So one thing we could begin with is considering this problem for platonic solids, the most classic and regular polyhedron we know of in 3 dimensions. And so we could think about this for a little bit, and we see that easily you could find a net, one of these legal unfoldings without overlap for each of the platonic solids. A brilliant twist on this was actually done in the work of Hojiyama and Shoji in their CCCG work in 2011 on edge unfoldings of platonic solids, showing that every possible unfolding along those edge cuts will give you a net. So in other words, for the cube, there are 11 different possible ways of unfolding it, and it turns out all of them are nets. None of the faces, none of these 6 squares overlap. And for the dodecahedron and the icosahedron, for example, here we see 7 possibilities for each of them, but it turns out there are 43,380 different unfoldings up to symmetry, and each of them give you a legal net. Beautiful work based on computational results. And what we want to do in this talk today is extend this to higher dimensions. So we want to consider unfolding polytopes, not just polyhedra. And so what does that mean? So far we've been considering edge unfoldings where we cut along edges and lay it flat from a 3-dimensional object flat into 2-dimensional plane. What we want to do is change this to the higher dimensional world. And the notion of an edge is now replaced with the notion of a ridge. So what we want to do is we want to take our polytope, cut along certain ridges, and unfold this polytope in a 1-dimensionless n-1 dimensional subspace so that the facets don't overlap. And so here are 5 examples of the 4-dimensional cube that unfolds into 3 dimensions. And it turns out that they're not just 5 of them, there are 261 distinct unfoldings of just the 4-dimensional cube into 3D. And we show in this work that all of them are without overlap. In other words, all of them form legal nets. And this is not just true for the 4-dimensional cube, but for every cube imaginable in every possible dimension. So how do we do this? Well, if we consider the combinatorics of this object, here's an unfolding of a 3D cube. And what's really interesting to us as we generalize this to higher dimensions is the skeletal structure, the 1-dimensional skeletal structure of the dual. So the dual of the cube is the octahedron, and here's the skeletal structure. And we're going to just redraw the skeletal structure in a different way. And that looks like this. So if we have these 6 faces of the net, these connected faces, you notice that in the dual they form a spanning tree. And the spanning tree is actually on the 1 skeleton. So we can redraw that spanning tree this way on this Roberts graph with 6 nodes. And in general, here's how the combinatorics looks. We take a generic Roberts graph of 2 n nodes. Each node corresponds to a facet of the n-dimensional cube, and we draw spanning trees on it. And those spanning trees correspond to the unfolded structure of this n cube in n-1 dimensional space. The catch is that as you unfold it in n-1 dimensional space, the unfolded structure is actually going to form a net without overlap. So there's a geometry behind the scene that the combinatorial spanning tree is going to give us some geometric unfolding structure. How do you get from the top picture, which is the spanning tree, to this underlying geometric unfolding? That's the question we want to talk about. And the moment we solve that question, we end up with the following theorem. Every ridge unfolding of an n-dimensional cube yields a net. The way this happens is the combinatorics of a roll. And this is how a cube unfolds. It rolls along in the n-1 dimensional space, stamping its facets on this n-1 dimensional hyperspace. And so we see that this roll rotates the 4 facets all along that axis of rotation, and it keeps invariant, and it fixes all the other facets. In particular, combinatorially, here's what it looks like on the Roberts graph. So you see that the 4 vertices that are involved, corresponding to the 4 facets, all cyclically permute, but all the other vertices are fixed. And here's an example of this rolling that's happening in 4D, a work of Jason Heiss from Wikipedia. That gives us the combinatorics, but we still need the geometry of what's going on. The geometric structure comes from a coordinate system we place. So for example, if you have a 3-dimensional cube and you want to unfold into 2-dimensional space, we put this coordinate structure along this Roberts graph. So the only catch is that this x1 coordinate and the negative x1 coordinate form, in some sense, this 90-degree angle along this Roberts graph. They're antipodal to one another. And similarly, the x2 coordinate and the negative x2 coordinate is also antipodal along this Roberts graph and form this 90-degree angle. And this is true for the 4-dimensional cube unfolding into 3D, or the 5-dimensional cube unfolding into 4D. We arbitrarily give it a coordinate structure x1 through xn minus 1. The only catch of arbitrarily positioning these objects in any coordinate system you want is to make sure you give its corresponding antipodal coordinate structure the negative of the coordinate that you gave it. As you perform your rolls, the coordinate structure stays fixed. It's only the labeling of the facets that permute cyclically along those rolls. So here's what the 3D object looks like. So this is a spanning tree that's been drawn, in particular it's a spanning path that's been drawn on the Roberts graph that corresponds to a 3-dimensional cube. Notice this thing has 6 vertices, so that's a 3D cube which has 6 facets. And this is the coordinate structure that's given to this Roberts graph. So we take this vertex, this is the edge that's inputted into this vertex, and as it gets put into this vertex, it rolls along this path right here. And notice that the direction in which we're rolling corresponds to the x1 direction. So we roll along the x1 direction, and the entire structure of the graph gets updated based on the new positions of the vertices that have moved, corresponding to the facets. And notice that the next object to roll is also in this direction here. The previous edge that was rolled from here to here now gets a dotted line, meaning it's accomplished its goal. And this vertex is now turned white, meaning that facet is no longer in use anymore. And now here's a new edge that we want to roll along. We again roll in the x1 direction, so we move in the x1 direction, we roll. So now the next edge that needs to be inputted is here. Now notice that is along the second x2 direction. So I stamp along that direction. And I continue to play this game, basically unrolling these edges through this based fixed vertex on the R2 plane. And this is the unfolding. So in other words, this is the net that corresponds to this spanning tree. The similar thing can be done in 4 dimensions. We just arbitrarily draw a spanning tree, and we arbitrarily give some coordinate system. We want x1, x2, x3. And the moment we have those two structures, the coordinate system is fixed, but the spanning tree is unfurled as we roll along the different coordinates that we want. And the unfolding takes us to this net. Now notice so far the 2 examples that I've given are both paths. Even if you don't have a path, if you have any arbitrary spanning tree, you use the exact same algorithm. But the catch is, given to any 2 vertices on your spanning tree, there exists a unique path between it. And all I'm doing is iterating that path structure for any 2 arbitrary vertices on your spanning tree. And it's going to work exactly the same way that I want. And here's our main result. It's based on one simple lemma. In the unfolding along some path of the spanning tree, if a direction x is used in one of your xn minus 1 coordinate directions, then the direction negative x will never be used along the path unfolding. In other words, the moment you decide to go in one particular direction, you can never make a U-turn and turn around and go backwards in that direction. And the proof is actually quite straightforward. The moment you realize that you pick a certain directions to go along, so in this particular case, let's pretend we're going along the x direction, the moment I form this roll, you notice that this vertex over here moves down, and this vertex over here moves over and has taken up this position. Now, if I want to perform a negative x roll, then this vertex has already been used, and it can't go back to this original position. That vertex, which corresponds to a facet, has been stamped on that hyperplane. which means the only way to go to a negative x roll is to actually get something here instead of this used vertex. But there's nothing that can actually move this vertex other than rolls, since this entire unfolding is based on rolls. Of course, there's one way to get this negative x out of here, which is to perform another x roll, which means that this will move over here, but this used position will move into this negative x position, and thus you're always fixed with some facet that has already been stamped. Because of this, it immediately follows that every ridge unfolding of an n cube yields a net, because the moment you move in a direction, you could never make a U-turn. So here's how the proof goes. Given any spanning tree, choose a path in that spanning tree. Along this path, you will only be increasing the distance between the initial position and the final position. And if it's only going to be farther and farther away, then you will never have overlap. And based on this, we notice a couple of beautiful corollaries that come up. If you look at some of these unfoldings, you see that they fit into a nice bounding box. These are different boxes that fit for an unfolding of a 4 cube in 3 space. And so we have this definition we call an n cube partition simply an integer partition. We take the number 3n minus 2 and we shatter it into n minus 1 parts, where each part has to have at least 2. And so, for example, if you look at the top, you see that for the 4 cube, 3 times 4 is 12 minus 2 is 10. So I take 10 and I shatter it into 4 minus 1, 3 parts. So I take 10, break it into 3 parts. Each part has to have at least a 2. So 6, 2, 2, 5, 3, 2, 4, 4, 2, and 4, 3, 3 are the only ways you can shatter that. And you see that your unfolding fits into one of these 4 boxes. So we see this theorem for every net of an n cube. The dimensions of a bounding box is an n cube partition. Now, the converse of this theorem is also true, and we get the bounding box partition theorem, which says for any n cube partition that you give me, I'm able to find a path unfolding of an n cube, a net whose bounding box dimensions matches the partition that you give me. Both of these theorems, the partition and the packing theorem, the proof is given in the CCCG paper. But there's an interesting remark that follows from this. Note that the n cube can be unfolded into these 2 extreme cases based on the partitions you give me. One is a partition of an n plus 2, 2, 2, 2, 2, 2 partition, extremely long, thin box, or the other end of it, a cube-like 4, 3, 3, 3, 3 box. And in fact, you get a whole spectrum of sizes between based on the partition that you have. And it's an open problem to find out the actual distribution of the cube partitions over all possible unfoldings of the n cube. For the 4-dimensional cube, we saw that there were 4 different partition examples. In which ways do the 261 unfoldings of the 4D cube land in one of those 4 partition examples we saw earlier? It's an open problem. And finally, let's close with thinking about regular convex polytopes in general. We know for the regular convex polyhedra, we have the 5 platonic solids, and the higher dimensional analogs fall into 2 groups. One, there are 3 classes of such polytopes that exist for all dimensions: the simplex, the cube, and the orthoplex, the dual of the cube. This paper shows that the unfolding of the cube always yields a net. It's not too difficult to show the same thing for the simplex. And the notion of the orthoplex and its net structure is quite different than the arguments given above in these combinatorial structures. And that's something we're exploring right now. But not only are these 3 classes for all dimensions, there are 3 exceptional cases, and they appear only in 4 dimensions: the 24 cell, the 120 cell, and the 600 cell. And we believe that these can be approached and attacked using probably a computational method of exhaustion. And so we have this conjecture: every ridge unfolding of a regular convex polytope yields a net. We'll see what happens in the future. Thank you so much for your time and for listening to this talk.